This is a discussion of the properties of solutions, particularly the question of solubility. And I show here a picture of Devil's Sinkhole in Rock Springs, and we'll see if we can talk a little bit at the end about how these things are formed. What could cause huge holes in limestone like Devil's Sinkhole or natural bridge caverns? Now, we talk about saturation. When a solution is saturated with a solid, then the rate of solution is equal to the rate of crystallization. Even though nothing appears to be dissolving, something's continuing to go on. At some point, the water contains all the solute it can handle. All the solute it can solvate, remember the water molecules form around the ions at that temperature. The solid has become cations and anions in the water, but the cations and anions are also running into each other and turning into solid. And at that point, the rates of solution and crystallization are equal. We say it's at an equilibrium. The point we see here is a saturated solution. The concentration of the solute is as high as it can get at that temperature. Here's a picture showing you how the solvated ions can collide and go back to the crystal at the same time that the ions in the crystal are breaking up and dissolving in the water. The rate at which the solid dissolves equals the rate at which dissolved particles deposit on the solid whenever we have a saturated solution, a solution and solute at equilibrium. Now, at saturation, if you add more solute to the saturated solution, it'll just go to the bottom. Kind of like somebody with sweet tea who adds sugar to the tea, stirs the heck out of it, but still finds that the sugar falls to the bottom of the iced tea glass because it's saturated. Now, if you add more water to a saturated solution, of course, you reduce the concentration and it becomes an unsaturated solution. Solubility is expressed in grams per liter of solution or in grams per 100 grams of solvent. And we, of course, have to specify the temperature. Supersaturation, that's a little different. We can form a saturated solution of a substance, particularly things like sodium and potassium nitrate, at a temperature higher than room temperature, maybe 40, 50, 60 degrees Celsius. And then if we let it cool slowly without disturbing it, we may see the crystals don't immediately form. We call this a supersaturated solution. It's really got more in the water than it can handle in a low energy state. It's a high energy state. If we bump the solution, or if we add just one little crystal of that substance, the excess will come out. Sometimes even like a snowfall. So how would you determine the solubility of a salt? It's actually pretty simple. You add salt to water, keeping the temperature the same, until no more dissolves. Then you cover it and let it stand for a day or so to reach equilibrium and make sure that you didn't make a mistake and create an unsaturated solution. It could take a couple of days to do this. Then you filter out any of the residue, measure the volume of the supernatant of the actual remaining solution, and you evaporate the water from it to get the salt residue. You then measure the mass of the dry salt residue, you knew the volume or mass of the solvent that it was in, and that'll give you the solubility. It's a little bit involved, but it's doable. Now there's a point here about liquid and liquid mixing. Some liquids are miscible or mixable in any proportions. Water and ethanol, they're polar and polar. Benzene and kerosene, that's a nonpolar and nonpolar. Like dissolves like. Some liquids are partially miscible, some liquids are immiscible. Unlike liquids tend not to dissolve in each other. So benzene and water, oil and vinegar. And this is an oil slick that came off of a tanker that sank. And of course the oil floats on the water because it's immiscible. Going back to solids, here are what we call solubility curves. This is a very famous drawing. I've seen it for decades here. This shows the grams of solute per 100 grams of water at various temperatures. And you can see the gases all seem to have lower solubility at high temperatures. The solids, almost all of them, have a positively curving graph. In fact, you could read the temperature and saturated amount of solute in 100 grams right from the graph. Let's talk about gases for a minute. It doesn't surprise us that gases appear to have a lower solubility at higher temperatures. Remember, bubbles formed when we boiled water way below 100 degrees Celsius. That was air coming out of the solution. Higher temperatures mean more kinetic energy, so more movement of the water and the air molecules, so more bumping into each other, and more likelihood that the dissolved oxygen and nitrogen will be kicked out of the solution. That's of course why you make sure the air conditioning stays on if you're going to leave your fish tank for a day or so. They need the oxygen in there, and they need you to keep the aerator on, and they need you not to have a hot house or the oxygen will come out of solution and they won't be able to live. Remember, polar solvents dissolve polar solutes. So water dissolves alcohols, sugars, ascorbic acid, and other vitamins, except there are a few like vitamin A and vitamin D that dissolve in fat, which is why if you take a multivitamin, you should always have a little fat, some cottage cheese or something along with it. Nonpolar solvents dissolve nonpolar solutes. Again, oils dissolve these nonpolar vitamins. Kerosene dissolves oil-based paint. That's how you get that off your hands if you get any on yourself. Olive oil will dissolve the beneficial oils in herbs and make them more available to your body, or either when you eat them or when you rub them on your skin. And I just said oils and fats dissolve vitamins D and E. Water dissolves ionic solids, and gases have differential solubilities in waters, and that would be lower at high temperatures, higher at low temperatures. So, what could cause huge holes in limestone like Devil's Sinkhole or Natural Bridge caverns? And the answer is the rock dissolved in the carbonic acid that dripped down from above. The water from the rain made hydrogen carbonate ions out of the calcium carbonate, in other words, dissolved it, and that carbonic acid that formed from the water and carbon dioxide then is a very weak acid and can actually dissolve the limestone that it flows down into, and it can therefore make these big holes in the ground. If you want a really big hole in the ground, go see Carlsbad Caverns in New Mexico. The weak carbonic acid in groundwater filters into the limestone and dissolves it, making the sinkholes and the caves that we see in our area.